Okay, so what we're going to learn now is implicit differentiation, and we're going to understand why we want to use implicit differentiation to answer some questions. So the question that I've posed here is exactly a question that involves us using implicit differentiation, but let's first understand exactly what's being asked here, and let's use our knowledge and see if we can figure out why it is that implicit differentiation is useful. So here, this first thing is that this is the equation of a circle, okay, with radius 1 and center 0, 0. So this is 1, let's say this is 1, and then this is sort of our circle. Now, one thing we should note is that this is not a function, right? It's a relation, it's called. It's a relation between x and y. And the relation is graphed as this circle. So that's actually something that's going to come into play a little bit in a second, but we want to remember that this is not a function. It fails the vertical line test, right? That vertical line hits the curve twice, hits a circle twice. And again, just have it in mind that it's a relation. And why is that sort of important? Because now we take this point, square root 2 over 2, comma square root 2 over 2, and we're asked to find the tangent line to this circle at this point. So this point is like right here, okay? Where is this point? This point is right here. So let's get different color, and let's say this is the point. And then the tangent line looks like this. And if we're super clever, we can kind of eyeball it as first being negative, and if we're really clever, we'll know maybe it's -1. But okay, we're going to show that it's -1. It really is. And again, we want to find the tangent line to this relation at this point. So we're no longer talking about functions, and we want to use calculus even when we're not talking about functions, right? Again, this is just a relation, we call it. Now, how do we do this? One thing that we could do is that we could take this, and this is us not using implicit differentiation. We could take this relation, and we could solve it for y. So I'm going to get a minus x squared on both sides. I get y squared. And then I get y is equal to the square root of 1 minus x squared. And this is a little bit of a cheat because when I take the square root on both sides, I really got to put plus or minus. And with that being the case, right, again, this isn't a function. It's just the half circle if I take the plus part. So this is just the half circle. This is just this piece here. But, okay, I could then find the derivative, the way I normally find derivatives, y prime, right, is 1/2, 1 minus x squared to the -1/2 times -2x, right, by chain rule. The -2 is going to cancel. I'm going to get -x, 1 minus x squared to the -1/2. And this will give me the slope of the tangent line at any point x. I plug in this root 2 over 2, and I would get the slope of my tangent line, and then I'd have a point, and I could get the equation of the tangent line. Now, in this case, what I did was I algebraically solved for y. But as we'll see, it's not always possible to be given some relation and then solve for y. And let's go through this. Let's finish this. So what do we get? We're going to get that the derivative, right, if I call this f of x rather than y, f prime of x is equal to -x, 1 minus x squared to the -1/2. And then I plug in the point, the square root 2 over 2. Let's do some mental math. Take your time. It's going to be 1/2 over here, 1/2. Okay, so it's 1/2 to the -1/2. I have to figure out what that is. And then this is going to be -√2 over 2. So then this becomes, again, a positive -√2 over 2 times this negative to the -1/2, right? You can write this as then the square root of 2. And then this just becomes -1. And the slope is indeed -1. So take your time, verify that for yourself, and see that the slope will indeed be -1. And then you just use, whatever point slope or slope intercept y minus y1 is equal to m times x minus x1, and then now you have m, you have y1 is root 2 over 2 is equal to m negative 1 x minus root 2 over 2. And then this is the equation of this tangent line. Now, that's not using implicit differentiation. Let's go ahead and let's use implicit differentiation, because it's not always the case that I'm going to be able to solve for y. I may have to just look at the original relation and differentiate. And we need to just have some understanding here. So we got x squared plus y squared is equal to 1 is our relation. And we're looking at the point, we're looking for the slope of the tangent line at the point root 2 over 2, comma root 2 over 2. And what we could do is we could implicit differentiate using implicit differentiation. Okay, and what does that mean? Okay, it's using chain rule. It's just an application of chain rule if we're careful. We're going to be differentiating with respect to x. So the derivative of x with respect to x is 1. So what is the derivative of x squared with respect to x? It's the derivative of x squared, which is just 2x, times the derivative of x with respect to x is just 1. So I don't really need to put that times 1 there. I don't need to use that chain rule aspect. But here, if you look, y squared, right? Remember, y is equal to something with a bunch of x's. So here's a bunch of x's. Right? So y is a function of x. Right? Like in our case here, y is deliberately the square root of 1 minus x squared, and then we'd have to remember that it's plus or minus. But okay, that's how I would solve for y. It's some function, and then it's being squared. So how would I differentiate this? Well, I would bring down the 2, so I'm going to do plus the derivative of y squared is 2y times the derivative of y, which is no longer 1 because you're differentiating with respect to x. So the derivative of y, you could write it as dy dx or y prime is equal to the derivative of 1 with respect to x. The derivative of a constant is 0. And what you care about is this dy dx term, this dy dx thing here, because that's the derivative. Okay, you could write it as y prime, you could write it as dy dx, but dy dx is now becoming a little bit more clear that we differentiate dy with respect to x. That's what that means, dy dx. And we care about this. This here is the slope of the tangent line. And what point do we care about? We care about it at this point. So I could sit here and solve it for dy dx. I'll do that, that's fine. Minus 2x, right? And then I get 2y dy dx. And then I divide by 2y. And I get my relation. I get it's x over y is dy dx. And this will give me the slope of the tangent line at any point, given an x and a y value. So what's the x value? The x value is root 2. But it's negative, sorry. Root 2 over 2. Negative divided by root 2 over 2. And I get negative 1 again. Dy dx. And now I have the slope of my tangent line. And the same thing again. Y minus y1 is equal to m times x minus x1. And now I have y minus square root 2 over 2. Negative 1 times x minus root 2 over 2. And I'm done. I've got the equation of my tangent line. Similarly, but now let's go to why it is that we really want to use implicit differentiation when trying to find the slope of tangent lines and so forth. So we have another case. So let's say we have to find the equation of a tangent line. Find equation of the tangent line 2. And now I'm given this crazy relation, 3y squared minus 6xy plus 2x cubed minus 5y is equal to 2 at 2, 1. Okay, and in this case, if you tried to solve for y, it would never work. It's impossible to solve this for y and then differentiate. So you have to implicit differentiate this to get the answer to this. So implicit differentiate, and you just sit here and you differentiate term by term. You have to remember that the derivative of y is not 1 when you're differentiating with respect to x. So I'm differentiating with respect to x, so the derivative of y is dy dx. So what's the derivative of 3y squared? Well, the 3 still comes out, times, what's the derivative of y squared? You bring down the 2, times y to the 1, times the derivative of y by chain rule. So that's dy dx. That's the derivative of y with respect to x. Minus 6 times. Now, this one's tricky because now here you need to see this as a product. Okay, so it's the product of x and y. You need to use product rule. And again, you need to remember the derivative of y with respect to x is dy dx. The derivative of x with respect to x is 1. So using that fact, right, this is like your f, this is like your g, and then you say the derivative here is going to be f prime times g plus g prime times f. So what is it going to be? It's going to be the derivative of x is 1 times g is y plus, and this is all minus, make sure we put the brackets in the right way, plus the derivative of g is the derivative of y, so it's dy dx, times f is just x, plus, then I'm just going to get the 6x squared times the derivative of x is again 1 minus 5 times the derivative of y, dy dx, is equal to 2. Now, you could sit here and you could solve it. This is not y prime, it's just y. You could sit here and solve it for dy dx. You could group them together, move them around, and get everything done. You could do that. That's fine. But what I'm going to do is this instead is that I'm just going to plug in this point. This is an x value. This is my y value. And then I'll solve for dy dx because it'll be a lot easier. This is just 6 times 1 dy dx minus 6 plus dy dx times 2 plus 6 times 4 is 24 minus 5 dy dx is equal to 2. But I didn't differentiate this. This is supposed to be 0 because the derivative of a constant is 0. So, sorry, this shouldn't be 2. This should be 0 over here, 0. And then now I'll sit here and make it a little bit easier for myself. This is 6, and I can call this y prime to make it quicker, minus 6 plus minus 2y prime plus 24 minus 5y prime equals 0. The like terms are going to give me 18, negative 18 on this side. And then over here I got y prime as just negative 18, which means that the slope of the tangent line at this point is just negative 18. I write my equation y minus y1 equals m times x minus x1. I have y minus 1 is equal to negative 18 x minus 2, and I'm done. This is the equation of my line. Now, where did I mess up? 18 over 11, did I mess up? I had 18, 5. Okay, I made a mistake somewhere, but this is the general idea of how this is done. So correct my mistake.